Hello everyone, I'm Linda Dotto de Moraes from the Federal University of Santa Maria, and I'm going to present my paper, which is called Deep Reinforcement Learning Techniques from Long-Dimensional Sensing Mapless Navigation of Terrestrial Mobile Robots. This presentation is divided in introduction, theoretical background, experimental setup, methodology, results, and finally the conclusions. As an introduction, in this paper we present two deep reinforcement learning approaches to enhance the problem of mapless navigation for a terrestrial mobile robot. In this case, we are using the Turtlebot 3. It has to navigate avoiding obstacles until it gets to a specific target that we set. And deep reinforcement learning is when we apply deep learning to reinforcement learning. The robotic field has an intrinsic relation with reinforcement learning, since many algorithms had already been developed for a range of tasks to teach an agent to learn a perfect set of actions through trial and error interactions. With that in mind, in this paper we compare two deep parallel algorithms, the DeepQ network and the double DeepQ network. Here in the image, we show the environment and the proposed architecture. The approaches are based on the simple sensing idea with 26 samples for the state, arranged by 24 laser sensor readings. One is the distance to the target, and the last one is the angle to the target. Comparing to these two algorithms, we also aim to show how double queue architectures perform when compared to the simple queue architectures. As a theoretical background, first we have obviously DeepQ network, which is an algorithm that applies concepts of reinforcement learning, such as Bellman equation, and it's given by this first equation. This equation is based on a state action pair. As you can see, S stands for the state and A is the action. So this first equation returns the optimal value given a pair of state action. Employ a neural network with weights, and the weights here are represented by theta. So employing it as a function approximator to estimate the action value function in the Bellman equation, we guarantee the convergence to the optimal value. This neural network can be trained by minimizing a loss, and here I present the loss equation, with y being the target function that employs the network weights from the t episode, and it's used to create a temporal difference between the value found and the expected value. So this is basically the DQN. But it has a problem. The max operator employs the same values for selecting and evaluation an action. So this can lead to choosing overestimated values, and these overestimated values lead to overly optimistic value estimations. So as a potential solution, we have double DeepQ network, which uses a double estimation approach to estimate the value of the next state. And this is our new target function with two queues. For the experimental setup, we have PyTorch, and I guess most of you already know PyTorch. It is an open source machine learning library in Python. Here it's used to create deep neural networks. We also use ROS, and if you study or work in robotics field, you may know ROS as well. ROS stands for Robot Operation System, and it's an open source middleware that manages the connections between software and hardware in robots. It is not an operational system, but it provides some operational system standard services like messages and processes. And Gazebo is a support tool that we use in ROS for simulated experiments. It is a 3D simulator. The screen captures of the robot in the simulated environments you're going to see in the presentation are from Gazebo. The robot used in our case is Turtlebot 3. Here I show an image of the real one. Turtlebot 3 is a mobile robot from the robotics company with Raspberry Pi 3 development hardware, which makes it really good to use. And these are the simulation environments in Gazebo, like I said. In the scenario, also refers to as stage 1. It has no obstacles, and the second one has 4 cylinders as obstacles, and the third one has white blocks. All those obstacles are fixed. So as you can see here in the third one, we were trying to add a little bit of complexity compared to the other two. Now I'm going to talk about methodology. Here I present the Q network used in both DQN and double DQN. It has 26 inputs, like I mentioned in the introduction. Each fully connected layer has 256 nodes and a relay activation. We also use a dropout layer, as you can see. The output is a discrete number between 0 and 4, and it's equivalent to the angular velocity. I will talk about the angular velocity in the next slide. The linear velocity is 0.15 meters per second, and there's no backward move. About the angular velocity, here I bring the relation between the output actions and the angular velocity. If the output is 0, the angular velocity will be minus 1.5 radians per second, which means the robot will turn to the right. If the output is 2, the boat goes ahead. In our case, we have only those 5 possible angular velocities. Now, for the reward, we have 3 types of rewards. If the robot collides on the walls or on the obstacles, it gets 20 negative as a reward. If it hits the target, it receives 200 as a reward. There's also a needle condition. When the robot doesn't hit the target, neither collides in a range of 500 steps, it receives 0 as a reward. Finally, here are the results. First, I present you the training results, which is the learning through time. These are the moving averages of the reward when training the robot in each approach. In stage 1, the first scenario, we trained the robot for about 3,000 episodes. And in stage 2 and 3, the second and third scenario, we trained the robot for about 5,000 episodes in each approach. The result of the DQN algorithm is in blue, and the result of the double DQN is in pink. And here are the test results. For the tests, we set 4 fixed goals and performed 100 trials in each pattern model. So 100 trials and 4 goals, we get 25 trials for each fixed goal. This is the navigation behavior in each approach. Also, I recorded a total of successful trials and the average navigation time and their standard deviations as well to compare the results. So here are the episode times and the success rates. When the success rate is 100%, it means that the robot got to the target all the 100 trials. In the results of the third environment, we can see that double DQN has a better performance. As conclusions, we can see that double Q algorithms are capable of providing good performance even in relation to sophisticated deep RL algorithms. An interesting conclusion as well was the stable pattern of the learning process shown throughout different scenarios, and the time showing small signs of typical deep RL problems like gradient convergence or the forgetting. And finally, more studies on the way to confirm this pattern through other types of mobile robots and DeepRL techniques as well. And here I finish my presentation. Thank you for watching and listening, and you can contact me by email if you want for further information. Bye.